Welcome, everyone, to another deep dive. Great to have you with us. When we think about electric vehicles, our minds usually jump straight to the cool designs, maybe the quick acceleration or, the battery range. But underneath all that, there are some really critical parts doing the heavy lifting, components that, frankly, don't get talked about much. So today our mission is to sort of pull back the curtain. We're going to explore two incredibly vital but often overlooked parts of an EV, the inverter and the DC-DC converter. We've sifted through quite a stack of research for this, lots of sources you provided, covering everything from technical specs to some really interesting design choices. So the plan is to get a handle on what these things do, how big they actually are, and the clever, sometimes tricky ways car makers integrate them. It's about appreciating that hidden engineering.
Okay, let's unpack this. Let's kick off with the inverter. This is the component that, well, literally gets the motor spinning. You've got all that high voltage direct current DC stored in the car's main battery, right?
Right, the big battery. Yeah. But the motor itself, it can't just use that DC power directly. So the inverter's job, and it's absolutely crucial, is to change that DC into alternating current AC. That's what the motor needs to actually move the car. Without it, your EV is basically just a very stylish, very heavy paperweight.
And it's more sophisticated than just flipping a switch from DC to AC. What's really key here is the precision. The inverter doesn't just create AC. It carefully controls the frequency and the voltage of that AC.
Ah, okay.
Think of it like a conductor leading an orchestra. It tells the motor exactly how fast to spin and with how much force or torque.
So it's really dialing things in.
Precisely. This gives you that super smooth acceleration, the quiet cruising, and it's even essential for things like regenerative braking, capturing energy back when you slow down. It's the brain controlling the motor's muscle, really.
That's a great analogy, the conductor. Okay, so the inverter handles propulsion, makes the car go. But what about everything else? The lights, the wipers, the touchscreen, all the stuff that makes a car usable day to day.
Yeah, good point.
That's where the DC-DC converter comes in, I gather.
Exactly. That's its role.
It takes that same high voltage from the main battery.
Yep, the 400 volt or maybe 800 volt system.
Right, and steps it way, way down to much lower voltages that all the accessories use. Usually 12 volts, sometimes maybe 48 volts.
That's it. You absolutely need that lower voltage. You just can't run, say, your headlights or the infotainment system directly off the main traction battery.
Right, that would not end well.
No. It'd be like plugging your phone into a substation.
Yeah.
So all the standard car electronics, interior lights, power windows, power steering, safety systems like airbags, ABS brakes, they all rely on that stable lower voltage. The DC-DC converter is basically the car's internal power adapter. It makes sure everything that isn't the main motor gets the safe, steady power it needs. It's completely essential for, well, the whole driving experience.
Okay, so functions are clear. Inverter for go, DC-DC for everything else. But what about size? Are these big, heavy boxes taking up loads of space? Or has EV design managed to shrink them down?
Well, looking at the sources, it seems like compactness is a huge priority. The inverter, for instance, isn't enormous. Think maybe like a medium shoebox, or maybe a small, dense piece of luggage. We're talking dimensions like, say, 20 to 30 centimeters long, maybe 20 wide, and 15 to 20 high, somewhere in that ballpark.
Generally, yeah.
And they're engineered to be as small as possible. A big factor there seems to be liquid cooling. These things generate heat, so efficient cooling lets them stay small but powerful.
That's absolutely right. Managing heat is critical. Now, compare that to the DC-DC converter. It's usually much, much smaller than the inverter.
Okay.
Think more like a thick textbook, or maybe a power brick for a hefty laptop. Maybe 10 to 20 centimeters square, and often just a few centimeters thick. It's designed to be tucked away easily.
Right, quite a difference. And the reason for that difference is pretty straightforward, really. It comes down to power. The inverter is handling the massive energy flow needed to drive the wheels. That means bigger electronic components, more heat to manage, so it naturally ends up being larger and heavier.
Makes sense.
The DC-DC converter is dealing with much lower power levels for all those accessories, so it can be significantly smaller and lighter. But, both are designed with integration in mind. They're often placed near the motor or in specific housings to make the wiring neat, optimize the cooling, and just generally use space efficiently.
Okay, that makes sense. But our sources also mentioned something really interesting design-wise, a trend towards actually integrating the inverter right into the motor housing itself. Here's where it gets really interesting.
Ah, yes, the integrated drive unit approach. It's becoming quite common.
So what are the big advantages manufacturers are chasing with this? Why combine them?
Well, there are several key benefits driving this. First off, and maybe most obviously, is reduced size and weight.
Right, one box instead of two, basically.
Exactly. You get rid of a separate housing for the inverter, and you shorten or eliminate a lot of the heavy, high-voltage cables connecting them. That makes the whole powertrain unit more compact and lighter.
Okay, lighter and smaller. What else?
Improved efficiency is another big one. Shorter paths for the electricity to travel between the battery, inverter, and motor mean fewer electrical losses. Less energy wasted as heat. It's like having a more direct pipe for the power.
Fewer losses, so potentially more range.
Potentially, yes,
Yeah.
or better performance for the same energy. Then there's optimized thermal management. Because they're physically together, the inverter can often share the cooling system with the motor. They can help manage each other's temperature, which can be very efficient.
Ah, nice synergy there.
Definitely. And finally, it can lead to reduced complexity and potentially lower accessory costs. Less wiring, maybe fewer connectors, fewer separate protection devices needed. It can simplify the overall system.
Wow, okay. Reduced size, weight, better efficiency, shared cooling, simpler system.
Hmm,
That sounds like a pretty compelling list of pros.
it is.
So for the listener, what does this actually mean when they're driving an EV? How do these engineering wins translate? Because it sounds pretty significant.
Oh, it is. It's definitely not just a minor technical detail. What's fascinating here is how it enables progress. Lighter powertrains mean manufacturers have more flexibility. They can design smaller city cars that still feel peppy, or they can use the weight savings to pack in more battery for longer range without making the car feel heavy.
Right.
So for you, the driver, it translates into potentially better vehicle handling because it's lighter, maybe slightly longer range from that efficiency gain, and possibly down the line, a lower purchase price because manufacturing might be simpler or use fewer materials. It's one of those background innovations that's really helping push EVs forward, making them more practical and appealing.
Okay, so if integration is so great, why isn't every single EV built this way? There must be downsides, right? Because engineering is always about trade-offs.
You've hit the nail on the head. It's always a balancing act. And yes, there are definitely disadvantages or limitations to consider with integration. The first one is configuration rigidity. If the inverter is physically part of the motor block, it's much harder to swap out just one of them.
Ah, for repairs or upgrades.
Exactly. If the inverter fails, you might need to replace the entire integrated motor inverter unit, which could be more costly or complex than replacing a separate component.
Okay. That makes sense.
Then there's the potential for cooling challenges. While shared cooling can be an advantage if it's not designed really well.
It could be a problem.
It could. You've got two major heat sources, the motor and the inverter packed tightly together. Managing that combined heat load effectively in a confined space is a serious engineering challenge. Get it wrong, and you risk overheating.
Right, concentrating the heat sources.
Precisely. Third, it can impact maintenance and repairs in general. Even if just one part needs attention, mechanics might have to disassemble or remove the entire integrated unit to get access. That could mean longer repair times and higher labor costs.
More complex servicing?
Potentially, yes.
Yeah.
And finally, there can be design constraints. The physical space available inside the motor housing might limit how big, and therefore how powerful, the integrated inverter can be. For very high-performance applications, a separate, larger inverter might still be necessary.
So this raises an important question. How do manufacturers decide? Integrate or keep them separate? It sounds like it depends heavily on the specific car.
Absolutely. It's a strategic choice based on the vehicle's goals. We're seeing many new EVs and hybrids really embracing integration because those benefits, the compactness, the efficiency, the potential cost savings are very attractive, especially for mass market vehicles.
Makes sense for volume production.
But for other vehicles, maybe high-end performance cars or vehicles designed for extreme modularity or perhaps easier field servicing, manufacturers might stick with separate components. It gives them more flexibility. It really highlights that continuous innovation and the different paths engineers take to optimize these incredibly complex machines.
So what does this all mean? Well, it means these components, the inverter and the DC-DC converter, even though they're relatively small and you probably never see them, are absolutely fundamental. They're the unsung heroes, making sure power gets where it needs to go efficiently and safely. And these design choices, like whether to integrate them or not, show just how much clever engineering is constantly happening under the skin of EVs. Maybe take a moment next time you see an EV. Consider how this relentless drive for compactness and efficiency in these hidden parts is what's making electric cars better, more affordable, and more practical for all of us. It really makes you wonder, doesn't it, what other invisible tech is quietly shaping our future? Anyway, this has been a really insightful deep dive. If you found it useful, we'd really appreciate it if you gave this video a like and subscribe to the channel. It genuinely helps us keep doing these deep dives.
Yeah, definitely. And please do leave your comments below. We're genuinely interested to hear what you think about these components, or if you have other EV tech questions you'd like us to tackle. We love reading your thoughts.
Thanks for joining us.